Hello and welcome back to Calculus, the series where we explore volumes and areas. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Today, we will begin looking at how to find the volume of irregular 3D shapes using integrals. However, before we get to actual examples, first, I'd like to show you the intuition behind the theory. So, first and foremost, I would like to begin with the visualization of a function f of x equals to 2x. Now, I want you to imagine that this function started rotating around the x-axis, with its end still fixed at the origin. This is what we call revolution. If you imagine this from a 3D perspective, a cone would be formed. However, we do not use the formula for the volume of a cone because what if the function were more complex? Let's say a function like this, and then the volume you would get would be much more complex and much more difficult to compute with just a formula. So that means we need a common way to find the volume of any shape, no matter how they look. Please recall that for the area under the curve, we used thinner and thinner rectangles, which were then added up to approximate and calculate the area under a curve. For volumes, a similar principle is applied, only instead of rectangles, we use cylinders. Now imagine that this cone shape now contains an infinite number of thin cylinders whose volume, when added up, would be the volume of the cone that was formed. However, for now, let's just take one of the cylinders. In order to find the volume of a cylinder, a formula is used, and it is pi r squared times h, where h is the height of the cylinder and r is the radius. Now, if I flip the cylinder, the height here would simply be this blue part. Technically speaking, this blue part on the graph is just a small movement along the x-axis, a change in the x-axis. Writing that mathematically would be dx. And now the radius. Here, this red line would kind of denote approximately the radius of our cylinder. However, in the graph for the approximation of volume, the function itself, f of x, is the radius. However, for one piece, one single cylinder, only a piece of the function which corresponds to the cylinder, meaning a piece of the function that corresponds to the cylinder is its radius. So technically speaking, in general, the function f of x itself is the radius of all cylinders, just at different parts of the x-axis. So now, when we piece it all together, the volume of this single cylinder could be written as pi times our function f of x squared and times our height dx. And finally, I need the volume of all cylinders combined. Just like with the area, we can use the integral from one bound to another. I could use the integral from a to b of our entire expression for the volume of one cylinder. Let's show you an easy example just with the function that was given to us, f of x equals to 2x. Let's say this function was rotated around the x-axis by 2 pi radians, in other words, 360 degrees, and we're asked with calculating the volume from 0 to 2. Applying the formula for volumes of revolution, our integral would be from 0 to 2. Pi is technically just a constant, meaning we can always put it in the front. And now we need to raise our function 2x to the power of 2 and evaluate this integral. So technically what we're calculating is pi times the integral from 0 to 2 of the function 4x squared dx. By now, you guys are already mastered at this, so that means the antiderivative function you already know is 4x cubed over 3 evaluated from 0 to 2. We only have to plug in 2 and calculate because plugging in 0 will just give you 0. Inside we get 4 times 8, which is 32 over 3, and in front times pi. So that means the volume would be equal to 32 over 3 times pi. To conclude the video, I will tell you this. There is volume formed by rotating the function around the x-axis like we did just now. And actually, there is also volume formed by rotating around the y-axis. The two have a slight difference in calculation, and I will show you with examples in the next video. Also, just like with area, volume can also exist between two functions. Probably not the best visualization, but you get the idea. The idea would be the same as area between two functions. You take the upper function, subtract the lower, and calculate the integral from their intersections. However, we'll leave that with specific examples in the next video, so I hope to see you there, and have a nice day. Bye!